students. Last class we discussed about different types of enthalpy, Hess's law, application of Hess's law, etc. Today we are going to discuss about second law of thermodynamics. Second law of thermodynamics. Second law of thermodynamics. Now, before studying about second law of thermodynamics, what is the need for second law of thermodynamics? What is the purpose or what is the need for a second law? We have already discussed about first law of thermodynamics. First law states that energy can neither be created nor be destroyed. It can be transferred from one form to another. Okay, now what is second law and why do we need a second law of thermodynamics? So before discussing about the need of second law of thermodynamics, in thermodynamics we may encounter two types of process. We may observe two types of process. First one is spontaneous process and second one is non-spontaneous process. In thermodynamics we may see two types of process: spontaneous process and non-spontaneous process. Spontaneous process is also known as feasible process. Now what is spontaneous process? Spontaneous process means a process which takes place by itself or by an initiation. A process which takes place by itself or by an initiation are known as spontaneous process. Example, if I am placing a piece of ice here, it will spontaneously melt to form water, right? Here I am not giving any external energy, I am not supplying any external force or energy. Here ice is spontaneously, without any external help, ice spontaneously converts to water. So process which take place by itself. So ice by itself it is melting to water. So process which take place by itself or by an initiation are known as spontaneous process. Few examples for spontaneous process are flow of water from high altitude to low altitude. Water will flow from high altitude to low altitude by itself. It don't need any external pressure or any external force, right? So flow of water from high altitude to low altitude is an example for spontaneous process. Second example, dissolution of water. For example, if I'm adding NaCl, if I'm adding NaCl, okay. Consider this cup filled with water and I'm adding NaCl, a pinch of small amount of NaCl to this water. With time, this NaCl will dissolve in this water. NaCl will dissolve in this water by itself. I'm taking a glass filled with water and I'm adding a pinch of small amount of sodium chloride. Okay. With time, that NaCl will dissolve in water. That means here NaCl dissolves in water by itself. So dissolution of common salt, that is common salt dissolved in water. That's an example for spontaneous process which take place by itself or by initiation. Neutralize, reaction of NO and O2 giving NO2. Now I'm taking a closed cylinder, okay, closed and it is filled with NO and O2. Okay, by itself they react to form NO2. 2NO plus O2 giving 2NO2. So formation of N2 from NO and O2 is an example for a spontaneous process. So I'm filling a cylinder with oxygen and NO, nitric oxide. The cylinder is filled with oxygen and nitric oxide. They two react by itself to form nitrogen dioxide. So this reaction is an example for spontaneous process. Neutralization of acid and base. NaHCl is an acid, NaOH is a base. So neutralization reaction between acid and base to produce, when NaOH and HCl react, they produce NaCl and H2O. So neutralization reaction of base and acid is an example for spontaneous process. They take place by itself. When we mix acid and base, they react spontaneously. They react by itself. So that means they are spontaneous process. I think it's clear. Reaction of H2 and O2 to form H2O by initiation of electric spark. Now, if we mix H2 and O2, I'm taking a cylinder, I'm taking H2 and O2 here. They won't react to produce water. But when we supply electrical spark for 1 or 2 seconds, that is the initiation energy. When we supply an initiation energy, then they will react to form water. So when we supply an initiation energy, they react spontaneously. They react by themselves. So you can consider this reaction as spontaneous because process which take place by itself or by an initiation. So here I am supplying electric energy for 1 or 2 seconds. This is the initiation energy. After supplying initiation energy, they will react to produce corresponding water. So a process which take place by itself or by any initiation, those processes are spontaneous process. For example, burning of paper is an example for spontaneous process. So burning of paper, consider a paper. Okay, now if I am supplying heat energy here, that is the initiation energy. If I am supplying heat energy, okay, that is the initiation energy. After supplying heat energy, then the heat will burn, or that heat will burn the paper completely, and first I am giving an initiation energy. After that initiation, the paper is getting burned, right? So you can consider this reaction as a spontaneous process. I am supplying an initiation energy. After supplying initiation energy, the paper will burn. So this process is an example for spontaneous process. Aging is a spontaneous process. Aging will take place by itself. So aging is a spontaneous process. So spontaneous process are process which take place by itself or by an initiation. I think it's clear. Now there is another set of reactions. Those reactions or those processes are known as non-spontaneous process. Process which can neither take place by itself nor by initiation. So a process which cannot occur by itself are known as non-spontaneous process. For example, flow of water from low altitude to high altitude. Flow of water from low altitude to high altitude. Water will not flow from low altitude to high altitude, and that is possible when we supply electric energy. By using motor, if we supply electric energy, then the water will flow from low altitude to high altitude. But this is possible only in the presence of external energy. We have to supply external energy. We have to supply electric energy to motor. So the motor will pump water from low altitude to high altitude. Okay, when you switch off the electrical energy, the motor will stop working. At that time, this process will stop. Okay, so this is not a spontaneous process. We are supplying energy to make that process or to make that reaction possible or make that process possible. We are supplying external energy. So process which cannot occur by itself are known as non-spontaneous process. Flow of water from low altitude to high altitude. This is not a spontaneous. That process is non-spontaneous because we have to supply electric energy. So the motor will pump water from low altitude to high altitude. When you switch off the motor, then the flow of water will stop. Okay, so non-spontaneous process. Another example is electrolysis of water to hydrogen and oxygen. Okay, when we electrolyze water, so here water is electrolyzed. Electrolysis means we are supplying electric energy to water. When we supply electric energy to water, water will start splitting to produce H plus and OH minus. Okay, from this we can split water to hydrogen and oxygen. So by passing electric energy we can split water, and from that after splitting we can produce hydrogen and oxygen. Or water is decomposed to produce hydrogen and oxygen by passing electrical current. Now this process is an example for non-spontaneous process. When you stop giving current, when you stop supplying electrical energy, the process will stop. Okay, so here the process will occur. Till you supply electric energy. The process will occur till you supply electric energy. When you stop supplying electric energy, the process will stop. That means this process is an example for non-spontaneous process. So in thermodynamics, we may observe two types of process, or we may encounter two types of process. First one is spontaneous process, and second one is non-spontaneous process. Process which take place by itself or by an initiation are known as spontaneous process, and process which cannot occur by itself are known as non-spontaneous process. These are the examples for spontaneous process. Non-spontaneous process: flow of water from low altitude to high altitude, electrolysis of water to produce hydrogen and oxygen, flow of air from low pressure to high pressure, flow of air always flow from high pressure to low pressure. Okay, low pressure to high pressure is not possible. We can make that possible by supplying external energy. So flow of air from low pressure region to high pressure region. So these are non-spontaneous processes. I think it's clear. Moving on to next topic. Driving force for spontaneous process. Okay, we have seen that there are two types of process in thermodynamics. Spontaneous process and non-spontaneous process. Process which take place by itself are known as spontaneous process, and process which cannot take place by themselves or itself are called non-spontaneous process. Now, why some processes are spontaneous? Only some processes are spontaneous. For example, flow of water from high altitude to low altitude, spontaneous. Then dissolution of sodium chloride, spontaneous. Aging, spontaneous. Why some processes are spontaneous? Now some other processes are non-spontaneous. For example, flow of water from low altitude to high altitude, that is non-spontaneous process. So reactions are of two types, spontaneous and non-spontaneous. Why some are spontaneous and why some others are non-spontaneous? Why some processes are spontaneous and why some others are non-spontaneous? Now, if we examine certain spontaneous process, we may realize that most of these spontaneous process have a driving force which lead them to be spontaneous. So if we examine some spontaneous process, we may observe that okay, these spontaneous process have a driving force. They have a driving force which make them to proceed in a spontaneous manner. Okay, for example, flow of water from high altitude to low altitude. This process is spontaneous. Why this process is spontaneous? There is a driving force. There is a force which drives. Drives means which helps. So there is a force here which helps the flow of water from high altitude to take place by itself. That force is known as driving force. So forces which helps a reaction to occur spontaneously without the help of any external force. Okay, forces which helps a reaction to occur by itself, that is spontaneously, without the help of external forces, are known as driving force. Now, if we examine spontaneous process, we can observe two driving force in each and every spontaneous process. If we examine a spontaneous process, we can observe two driving force. These two driving force helps a reaction to occur spontaneously. Which are the driving forces? First one is tendency to attain minimum energy. tendency to attain minimum energy. Tendency to attain minimum energy. Okay, this is the first driving force, tendency to attain minimum energy. Now, consider a reaction where reactant converted to product. Let the reaction be exothermic. Exothermic means here energy is liberated during reaction. Let the reaction be exothermic. That means energy is liberated during reaction. Let the heat energy is liberated during reaction. So consider a reaction where reactant convert to product, and if the reaction occur by liberating heat, then those reactions are exothermic in nature. For exothermic process, delta H is equal to negative. Right? You know that. Now, what is exothermic process? Exothermic process means when a reactant convert to product, heat energy is liberated. That means energy of reactant is greater than energy of product. Why? Because reactant liberates heat energy and converts to product. Reactant liberates heat energy and it's converted to product. That means energy of reactant is more, and it is liberating energy, so that energy decreases, that's why it is converting to product. So here energy of reactant is greater than product. So in exothermic reaction, energy of reactant is greater than product. I think it's clear. Now you know that energy and stability are inversely proportional. Okay, energy and stability are inversely proportional. As energy decreases, stability increases. As energy decreases, stability increases, because energy and stability are inversely proportional. So that means stability of product is greater than stability of reactant, because energy of product is less compared to energy of reactant. That means stability of product is greater. Stability of product is maximum than stability of reactant. So in all exothermic process, stability of reactant is less than product, or stability of products greater than stability of reactant, right? Because energy of product is less, so stability will be greater. So stability of product is greater. Stability of product is greater than stability of reactant. I think it's clear. Stability of product is greater than stability of reactant. So if stability is greater, means reaction has a natural tendency to convert to product, because stability of product is greater than stability of reactant. So reactant has a natural tendency to convert to product. Okay, this is the first driving force. Stability of product is greater than stability of reactant. That means energy of product is less. Tendency to attain minimum energy. I think it's clear. So exothermic process are exothermic. So during exothermic process, energy is liberated, so energy of product is less than energy of reactant, so tendency to attain minimum energy. As energy of reactant product decreases, stability increases. That means energy of product is less than reactant, so stability of product is maximum. So reactant, which is less stable, will convert to product itself, which is having more stability. This is the first driving force, tendency to attain minimum energy. I think it's clear. This is the first driving force, but this is not the essential driving force. This is not the essential driving force. Why this is not the essential driving force? Because some endothermic reactions are also spontaneous. Some endothermic reaction. What are endothermic reaction? In endothermic reaction, reactant will absorb energy to convert to product, right? Reactant will absorb energy to convert to product. So energy of reactant is less compared to energy of product. Okay, these are endothermic reactions, but some endothermic reactions are also spontaneous. So this is not the essential driving force. Consider ice melting to water. This is ice It's melting of ice. Okay, water. Now ice will melt to form water by absorbing heat energy. This is an endothermic process, and you know that this process is spontaneous. When you place a piece of ice here, this ice piece will melt to form water spontaneously. We don't want to give any external energy to that ice. It will spontaneously melt to water. It will melt to water by its own, right? So melting of ice is an example for spontaneous process. But this is actually an endothermic reaction. Here heat is absorbed. So this is not the essential condition. It may be one of the condition. It may be one of the driving force. It may be one of the driving force, but it is not the essential driving force. Second driving force is the essential driving force which make a reaction to occur spontaneously. Second driving force, the important driving force which make a reaction to occur spontaneously. So moving on to second driving force. Now second driving force is tendency to attain maximum disorder. Tendency to attain maximum disorder. This is the second driving force, and this is the essential driving force. Tendency to attain maximum disorder. This is the essential driving force which makes a reaction to occur spontaneously. Tendency to attain maximum disorder. Now I'll explain this with an example. Consider melting of ice. Melting of ice. Ice is a solid. In solid, particles are closely packed, right? This ice will spontaneously melt to form water by its own. Ice melts to form water by itself. That means spontaneous process. So ice spontaneously melts to form water, right? In water, water, liquid, right? Compared to ice, in water, molecules are having some degree of freedom. That means in ice, particles are closely packed. That means they are ordered. In liquid, particles are loosely packed. That means you can observe a disorder. So here ice will melt to form water, so that disorder of the system increases. Let ice be the system. Ice particles are orderly arranged, and when it converts to liquid, disorder increases. Now consider evaporation of water. Evaporation of water is another example for spontaneous process. Evaporation of water occurs spontaneously, right? Evaporation of water. When you place a cup filled with water, water molecule will evaporate spontaneously. Okay, so evaporation of water is an example for spontaneous process. Now, if you consider evaporation of water, during evaporation, so evaporation of water to give water vapor. Now water vapor is a gas. In gas, particles are further show disorder, or they are loosely packed compared to liquids. So in gas, particles are again loosely packed compared to liquids. That means disorder increases. So solid to liquid, or solid to liquid, disorder increases. Liquid to gas, again disorder increases. So in all spontaneous process, disorder always increases. If you consider melting of ice is an example for spontaneous process, and during melting of ice, disorder of the system increases. Evaporation of water is another spontaneous process. During evaporation of water, again disorder of the system increases. So if disorder of a system increases, then those processes are always spontaneous. Tendency to attain maximum disorder. If disorder of a system increases, then those processes always occur spontaneously. Melting of ice to water, disorder increases, spontaneous process. Evaporation of water to water vapor, spontaneous process, because disorder increases. So For every spontaneous process, disorder increases. For every spontaneous process, disorder increases. I think it's clear. So these are the two driving force. Which make a reaction to occur spontaneously. Tendency to attain minimum energy. Second one, tendency to attain maximum disorder. And second driving force is the essential driving force. I think it's clear. Moving on to next topic, entropy. Now entropy, it is represented by S. Now what is entropy? Entropy is defined as the property of a system which measure the disorder or randomness of a system. So it's a property. It's a thermodynamic property. It indicates the amount of disorder in a system. Disorder. Measure of disorder. If you consider this as the system, okay, the system will have some amount of disorder. Okay, the amount of disorder present in a system is represented by S. It's known as entropy. So, what is entropy? Entropy is defined as the property of a system which measure the disorder of the system, disorder or randomness. So it indicates the amount of disorder of the system. For example, if you consider liquid, water, in water, molecules are not closely packed, they are loosely packed so that they can move around. So in water or in liquid, molecules show some disorder, right? Because they are not orderly arranged. So they can show some disorders, right? So they will show some disorder because here particles or molecules are not orderly arranged. They are loosely packed so that they will show some disorder. Not orderly arranged, that means disordered. So in liquid, particles show some disorder. Let the disorder be yes. That disorder is known as the amount of disorder. The amount of disorder in a system is known as entropy. I think it's clear. Now, during a reaction, entropy will change. Entropy will change. During a chemical reaction or physical reaction, entropy will change. For example, if liquid evaporates to form gas, disorder increases because in gas, molecules are further loosely packed compared to liquid. That means disorder increases. Let the disorder of liquid be S1 and let the disorder of gas be S2. So when a reaction occurs, there is a change in disorder. So delta S be the change in disorder. Change in disorder can be calculated using this formula S2. Entropy of products minus entropy of reactant. Okay, so when a reaction occurs, there is a change in disorder. There will be a change in disorder. Either disorder will increase or disorder will decrease. There will be a change in disorder when a reaction occurs. Okay, the change in disorder, that is change in entropy, measure of disorder, amount of disorder is defined as entropy. So change in disorder or entropy, delta S is equal to entropy of products minus entropy of reactant. I think it's clear. Reactant is having some amount of entropy, product is having some entropy, both the entropies are not same. So when a reactant convert to product, there is a change in entropy. So delta S, change in entropy, is calculated using this formula S2 minus S1. I think it's clear. Now there is one more formula to calculate entropy. There is one more formula to calculate entropy, and that formula is, this is the first equation, and second equation is delta S is equal to Q reversible by T. Now, if a system absorb heat energy reversibly, so consider a system which show reversible process. And during that reversible process, if heat is absorbed at a temperature T, then entropy of system, delta S, entropy of system is equal to Q reversible by T. I think it's clear. Once more, consider a system, let this be the system. and the system is showing some reversible process. Let the system be showing some reversible process, right? We have already learned the reversible, irreversible process works, etc. So if the system is showing some reversible work or reversible process, and if system is absorbing Q amount of heat at a temperature T, then entropy of system, delta S system, that is delta S, entropy of system is equal to Q reversible by T. Actually, this equation is derived by doing so many steps, but we don't want to study, or we don't have derivation to study, so I'm just neglecting those derivation. Please learn this equation. This equation is derived from this reaction. This equation is derived from this reaction, but we are not at all concentrating in derivations. We have to study only equation. Okay, in your NCERT textbook, derivation is not given, so I'm skipping. I'm neglecting derivation. Please study this equation. So these are the two equations to calculate entropy change. Delta S is equal to Q reversible by T, and delta S is equal to S2 minus S1. Entropy of products minus entropy of reactant. First one. Delta S is equal to Q reversible by T. If a system is undergoing a reversible process, and if it is absorbing Q amount of heat at a temperature T, then delta S is equal to Q reversible by T. I think it's clear. Now, entropy is a state function. It's a state function. Okay, in our introductory part, we have already discussed about state function and path function. Entropy is a state function, and it is an extensive property. Extensive property. Extensive property is also discussed in our introductory part. So entropy is an extensive property and a state function. Entropy is an extensive property and a state function. Now, unit of entropy. Unit of entropy. Unit of entropy change. Sorry, unit of entropy change. Unit for delta S. Now, unit for delta S is Joule. Moving on to next topic, second law of thermodynamics. Now, second law of thermodynamics states that the entropy of the universe increases in the course of every spontaneous process. For every spontaneous process, entropy of the universe increases. For every spontaneous process, entropy of the universe increases. That is, delta S universe greater than 0. Greater than 0 means increases. Greater than 0 means increases. Less than 0 means decreases. So, second law of thermodynamics states that for every spontaneous, second law of thermodynamics states that the entropy of the universe increases for every spontaneous process. For every spontaneous process, entropy of the universe increases. I'll explain this statement by using two examples. Consider an isolated system. Consider an isolated system. What are isolated system? What are isolated system? System and surrounding. Between system and surrounding, there is no exchange of energy take place. That is, no exchange of heat energy takes place between system and surrounding. No exchange of heat energy takes place between system and surrounding. Let this be the system, and let this be the surrounding. So isolated system means isolated. So isolated system means there is no exchange of heat between system and surrounding. Now consider this isolated system. Now here ice is melting. Ice melts to form water. We know that ice melts to form water is spontaneous process, and during this process, what happened? Entropy increases, right? In ice, particles are closely packed. In water, water particles are loosely packed. That means entropy increases. For spontaneous process, ice melt to form water, that's a spontaneous process occurring in an isolated system. Entropy increases, right? Entropy of the system increases. Entropy of the system increases greater than 0. I think it's clear. So consider an isolated system. Isolated system means there is no exchange of energy take place between system and surrounding. Now, in this isolated system, ice is melting. Ice melts to form water. Ice is converting to water. Ice melts to form water. Now, we know that this process is spontaneous. And here, when ice melts to form water, entropy increases. So, in this isolated system, when this spontaneous process occurs, entropy of the system increases. Delta S system greater than 0. I think it's clear. Now consider one more example. Instead of isolated system, if I'm taking open system, what happen? Ice to water. Now I'm taking open system. This process is spontaneous. So entropy of system increases. We can write entropy of system increases. Because ice to water. Ice melts to form water. It's a spontaneous process, and during this spontaneous process, entropy of the system increases. But here, system and surrounding are in contact. They are in contact with each other. In previous case, we are considering isolated system. So, in that isolated system, entropy is increasing during a spontaneous process. But here, we are taking an open system. So, here, when ice convert to water, okay, the process is spontaneous, so the entropy of the system increases. Since system is in contact with the surrounding, entropy of surrounding also increases. Since system is in contact with the surrounding, entropy of surrounding also greater than 0. Okay, so during this process, entropy of system increases. During this spontaneous process, entropy of system increases. Since system and surrounding are in close contact, entropy of surrounding increases. Greater than 0, increases. So, we can write entropy of system plus entropy of surrounding increases. So, during spontaneous process or for spontaneous process, spontaneous process, entropy of system increases, entropy of surrounding increases. That means what is system plus surrounding? Universe, right? So, entropy of universe increases. What is system plus surrounding? System plus surrounding is universe. Entropy of universe increases. System plus surrounding is universe. I am writing here. I know. Okay. What is system plus surrounding? System surrounding means universe. That means entropy of universe, universe greater than 0. So, remaining part is here. So, it states that entropy of the universe increases for a very spontaneous process. So, we are conducting a spontaneous process in our system. Since system and surrounding are in close contact, entropy of system increases and entropy of surrounding increases. Entropy of system greater than 0, entropy of surrounding greater than 0. So, what is here? Both the entropies increases. Entropy of system and surrounding increases. So, entropy of system plus entropy of surrounding greater than 0 increases. What is system plus surrounding? Universe. So, entropy of universe increases. This is second law of thermodynamics. So, what is the need of second law of thermodynamics? Second law of thermodynamics relates spontaneity and entropy. Second law of thermodynamics, need of second law of thermodynamics. The need of second law of thermodynamics is that it relates spontaneity and entropy. So, for a spontaneous reaction, entropy of the universe increases. For each and every spontaneous process that occurring in nature, entropy of the universe increases. I think it's clear. This is second law of thermodynamics. I think it's clear. Moving on to next topic, Gibbs free energy represented by G. Gibbs free energy represented by G. Now, what is Gibbs free energy? Gibbs free energy is defined as the amount of energy available in a system to do work. It is the amount of energy available in a system to do work. Consider a system. Okay. Consider a system. Okay. the amount of energy available in the system, the amount of energy available in the system to do a work. Okay, that energy is known as Gibbs free energy. It is defined as the amount of energy available in a system to do work. So, Gibbs free energy is the amount of energy available in a system to do work. Okay, it is the amount of energy available in a system to do work. Now, why we are learning Gibbs free energy in thermodynamics? What is the purpose of learning Gibbs free energy in thermodynamics? Gibbs free energy is simply a method of telling whether a chemical process will occur or will take place spontaneously or not. So, by knowing the value of Gibbs free energy, we can predict whether a reaction is spontaneous or not. So, Gibbs free energy helps us to identify whether a reaction is spontaneous or not. Okay, I think it's clear. So, Gibbs free energy. Next topic is Gibbs free energy represented by G. Now, Gibbs free energy is defined as the total energy available in a system to do some work. This is the total energy available in a system to do some work or to do some process. This is the total energy available in a system to do some process. It is represented by G. Now, the purpose of learning Gibbs free energy in thermodynamics is that it helps us to predict whether a reaction is spontaneous or not. Gibbs free energy is simply a method of telling whether a reaction is spontaneous or not. Okay. Now, Gibbs free energy G is calculated using this equation. G is equal to H minus Ts. Gibbs free energy G is calculated using this equation. G is equal to H minus Ts. Okay. G is equal to H minus Ts. What is H? Enthalpy minus T temperature S entropy. So, Gibbs free energy G is equal to H minus Ts. Enthalpy minus temperature into entropy. Enthalpy minus temperature into entropy. This is G. Okay. Now, G is a state function. G value is a state function. It's a state function and an extensive property and an extensive property. So, Gibbs free energy is a state function and an extensive property. Okay, we already discussed extensive and state functions in our introductory topics. You can refer state function and extensive from the introductory topic. Okay, so Gibbs free energy is a state function and an extensive property. Okay, so what is Gibbs free energy? Gibbs free energy is defined as the total energy available in a system to do some process or work. Now, it helps us to predict whether a reaction is spontaneous or not. So, it is calculated using this equation. G is equal to H minus Ts. Now, please listen carefully. Consider a reactant system having H1 enthalpy and S1 entropy. Let the available energy in this reactant system be G1. This is the available energy, that is Gibbs free energy. Available energy in a system to do work, to do a process, work or process. Work is a process, so to do a work or a process. So, let H1 be the enthalpy and S1 be the entropy of reactant system, and G1, let G1 be the available energy in a system or available energy in the reactant system. Let the G1 be the available energy in the reactant system, that is Gibbs free energy. Now, during a reactant system changes to product system. Let enthalpy of product be H2, entropy of product be S2, and available energy inside this product system be G2. Okay, so during a process, reactant system changes to product system, or reactant converts to product. So enthalpy changes, entropy changes, and Gibbs free energy, available energy inside the system changes. Now, what does delta G, change in Gibbs free energy during the process? Change in Gibbs free energy is equal to Gibbs free energy of product minus Gibbs free energy of reactant, G2 minus G1. Now, delta G is equal to, what is G1? What is G1? G1 is, G is equal to H minus Ts. So what is G1? G1 is equal to H1 minus Ts1. What is G2? G is equal to H minus Ts2. So G2 is equal to H2 minus Ts2. Here temperature remains constant. Temperature remains constant. Here reactant is converted to product. Here reactant is converted to product at constant temperature. Constant temperature. Here reactant convert to product at constant temperature. So T remains constant. So G1 is equal to H1 minus Ts1. G is equal to H minus Ts. So G1 is equal to H1 minus Ts1. Temperature remains constant. And G2 is equal to H2 minus Ts2. Temperature again remains constant. So what is delta G? G2 minus Gibbs free energy of products minus Gibbs free energy of reactant. G2 is equal to, so G2 is equal to, what is G2? H2 minus Ts2 minus, what is G1? H1 minus Ts1, right? So delta G is equal to H2 minus Ts2, going to open the bracket, that it will become minus H1 minus plus Ts1, right? I think it's clear. So delta G is equal to H2, I'm taking this H1 here, minus H1, remaining minus Ts2 plus Ts1. I think it's clear till here. So what is Gibbs free energy? Gibbs free energy is the amount of energy available in a system to do some work or process. Okay. Now Gibbs free energy helps us to predict whether a reaction is spontaneous or not. G is equal to H minus Ts. Okay. Now consider a system. Reactant system changes to product system. Let G1 be the Gibbs free energy of reactant and G2 be the Gibbs energy of product. So delta G is equal to G2 minus G1. Now what is G? H minus Ts. What is G? G is equal to H minus Ts. So G1 is equal to H1 minus Ts1. G2 is equal to H2 minus Ts2. So I'm substituting those values. You will get delta G is equal to H2 minus H1 minus Ts2 plus Ts1. So I'm rubbing this part. Okay, I'm rubbing this part. I think it's clear till here. Okay, now delta G is equal to H2 minus H1. What is H2 minus H1? Delta H minus, okay, I'm taking T outside. Ts2 and Ts. I'm taking T outside. That is minus T. I'm taking minus T outside. So it will become S2 minus S1. Right? S2 minus S1. So delta H is equal to, delta G is equal to H2 minus H1 delta H. Minus, I'm taking minus T outside, so you'll get S2 minus S1. Minus T into S2, minus TS2. Minus T into minus S1, minus plus TS1. So delta G is equal to delta H minus T delta S. Delta H minus T delta S. I think it's clear. This equation is known as Gibbs equation. Gibbs. Gibbs equation. This equation is known as Gibbs equation. This equation is known as Gibbs equation. And this equation is also known as, this equation is having one more name, and this equation is also known as Gibbs-Helmholtz equation. Okay, this equation is also known as Gibbs-Helmholtz equation. I think it's clear. This equation is also known as Gibbs-Helmholtz equation. Okay, Gibbs equation or Gibbs-Helmholtz equation. In your NCERT textbook, this equation is given as Gibbs equation. Okay, so you can study this equation. So what is Gibbs free energy? Gibbs free energy is the total energy available in a system to do some work or process. Now, actually Gibbs energy, in thermodynamics we are studying Gibbs free energy in order to predict whether a reaction is spontaneous or not. Now, Gibbs free energy is calculated using this equation, G is equal to H minus Ts. Okay, now Gibbs free energy, delta G is equal to delta H minus T delta S. Okay, next topic, how can we predict spontaneity by using Gibbs free energy? How can we predict spontaneity, whether a reaction is spontaneous or not, by using Gibbs free energy? That is the next topic. So moving on to next topic, Gibbs free energy and spontaneity. Okay, Gibbs free energy is introduced to predict whether a reaction is spontaneous or not. Gibbs free energy is introduced, or we are studying Gibbs free energy in thermodynamics, is due to the it can use to predict, Gibbs free energy can use to predict whether a reaction is spontaneous or not. If delta G value is negative, then those process will be always spontaneous. If delta G value of a reaction is negative, then those process are always spontaneous. And delta G value is positive, then those process are always non-spontaneous. And delta G value 0, those process are equilibrium process. So by knowing the value of delta G, by knowing the value whether it is negative, positive or 0, by knowing the value of delta G, we can predict whether a reaction is spontaneous or not. So in thermodynamics, we are studying Gibbs free energy in order to predict whether reaction is spontaneous or not. If delta G value is negative, then those reactions are spontaneous. When delta G value is positive, then those reactions are non-spontaneous. And when delta G value is equal to 0, those reactions are equilibrium. Now, when we discuss this topic, a question may arise: why delta G value negative becomes spontaneous? When we study these values, or when we study this topic, a question may arise: why delta G value negative becomes spontaneous? Why delta G value positive become non-spontaneous? Why delta G 0 become equilibrium? So now next topic is, we are going to derive an equation, or we are going to derive delta G value, or we are going to prove delta G value negative indicates spontaneous process. So we are going to, in this topic, we are going to prove delta G value, when delta G value of a reaction become negative, then that reaction is spontaneous. So next topic is Gibbs free energy and spontaneity. In this topic, we are going to prove delta G value of a reaction become negative, then that process is always spontaneous. So please listen carefully. According to second law, what is second law state that for a spontaneous process, delta S universe greater than 0. For a spontaneous process, delta S universe greater than 0. This is the second law of thermodynamics. So second law of thermodynamics state that for a spontaneous process, entropy change of universe greater than 0. That is increases. Greater than 0 means increases. What is universe? Delta S universe means it is delta S system plus delta S surrounding, right? So according to second law of thermodynamics, for a spontaneous process, entropy of universe greater than 0, that is increases. What is entropy of universe? Entropy of universe means entropy of system plus entropy of surrounding. Okay, I think it's clear. Let this be equation 1. Okay. Now, consider a process carried out at constant temperature and pressure. So the process is carried out under constant temperature and pressure, where heat lost by the surrounding and gained by the system. So consider a process where a system absorbs heat energy from the surrounding. System absorb heat energy. Surrounding. So consider a process carried out at constant temperature and pressure. Here temperature and pressure remains constant, and the process is carried out at constant temperature and pressure, where heat energy is lost by the surrounding. So heat energy is lost by the surrounding and it is gained by the system. Now from the point of system is gaining heat energy. Now from the point of surrounding is losing heat energy. So you know that when a system or when a surrounding lose energy, then that energy is negative. Energy lost, negative. Energy gained, positive. If you consider exothermic reaction, in exothermic reaction energy is released by the system. Energy released. So delta H value negative. So negative indicate energy is lost or released. Here system is gaining energy. From the point of system is gaining energy, but from the point of surrounding is losing energy to system. So surrounding is losing energy to system. Okay, please remember that. Okay, surrounding is losing energy to system. Now, what is del? So I'm rubbing this one. I'm rubbing this topic. Now, entropy change of surrounding, delta S surrounding is equal to Q by T. Okay, entropy change can be calculated by the equation Q by T, right? I'm writing a negative here. Why I'm writing a negative here? Because surrounding is losing heat energy. Surrounding is losing heat energy at constant pressure. Surrounding is losing heat energy at constant pressure. Let it be QP. Heat at constant pressure. Pressure remains constant. QP. So surrounding is losing heat energy, so that heat energy liberated by the surrounding. So negative. Negative indicate heat energy liberated by the surrounding. So delta S surrounding is equal to minus QP by T. I think it's clear. Minus QP by T. Now, from the point of system, from this part, here system is accepting energy. Now we know that QP is delta H. We have studied the equation. Delta H is equal to QP. So from the point of system, QP is equal to delta H system, because QP is delta H, and here enthalpy of system increases because delta heat is absorbed by the system, so that enthalpy of the system increases. So this heat is absorbed by the system, so that enthalpy of system increases. That increased enthalpy with delta H system, right? QP is equal to delta H. We have already discussed this equation in enthalpy. Delta H is equal to QP. So this QP is absorbed by the system. So instead of QP, I can write delta H system. Substituting the value of QP here, we will get delta S surrounding is equal to minus delta H system by T. Delta S surrounding is equal to minus delta H system by T. I think it's clear till here. Please listen carefully. Here surrounding is losing heat energy. So QP amount of heat is lost by the surrounding. So entropy change of surrounding is QP by T. But I am writing a minus here in order to show that heat energy is lost by the surrounding by T. Now this QP amount of heat is gained by the system. So that what is QP? QP is delta H. So enthalpy of system increases, so QP will be equal to delta H system, because system is accepting that energy. Delta H system. Now substituting the value of QP in this equation, delta H surrounding is equal to minus delta H system by T. I think it's clear till here. Now substituting the value of delta surrounding in equation 1. Substituting the value of delta S surrounding in equation 1. So I'm going to substitute the value of delta surrounding in this equation. So equation will become for a spontaneous process. For a spontaneous process, delta S universe is equal to delta S system plus delta S surrounding. Instead of delta S surrounding, we can substitute this one, that is minus delta H system by T. So substituting the value of delta S surrounding in this equation, equation 1, for a spontaneous process, delta S universe is equal to delta S system plus, instead of delta S surrounding, we can substitute minus delta S system by T. I think it's clear till here. I think it's clear till here. I'm rubbing this part. So for a spontaneous process, delta S universe is equal to delta S system minus delta H system by T. Now I'm going to multiply those equations with minus T. So multiplying this equation with minus T, you will get, now multiplying this equation with minus T, you will get minus T delta S universe is equal to minus T delta S system minus delta H system by T into minus T. So we are going to multiply. Next step, we are going to multiply this equation with minus T. So we'll get minus T delta S universe is equal to minus T delta S system minus delta S system into minus T. Okay, I'm going to rub this part. Okay, I'm going to rub this part. Now, T and T cancel each other, minus minus plus, so you will get a minus T delta S universe is equal to minus T delta H system plus delta H system minus minus, this is minus, minus into minus plus. Now I'm going to rearrange this part. So minus T delta S universe is equal to delta H system minus T delta S system. I'm going to rearrange this part, my delta H system minus T delta S system. Okay, now minus T delta S system. Now what is G? What is Gibbs free energy? Or what is delta G? Delta G is equal to delta H minus T delta S. This equation is known as Gibbs equation. Gibbs equation, right? So according to Gibbs equation, delta G is equal to delta H minus T delta S. Now delta H system minus T delta S system. Okay, so instead of this one I can write delta G system, because delta H minus T delta S is delta G. So delta G system is equal to minus T delta S universe. That is, for a spontaneous process, we are starting with a spontaneous. For a spontaneous process, delta G is equal to minus T delta S, or we can write delta G is equal to negative for a spontaneous process, right? We start with from here. According to second law of thermodynamics, for a spontaneous process, then we write the equation. Then for delta S surrounding, we substituted minus delta S system. So for a spontaneous process, delta S surrounding, here equation is delta S surrounding is equal to delta S system plus delta S surrounding, right? For this, we substitute this one, and then we multiply with minus T, and after multiplying with minus T, we got this. Then from that we reach here. So for a spontaneous, according to second law, for a spontaneous process, delta S universe is equal to delta S system plus delta S surrounding, and for delta S surrounding we substituted minus delta H system by T. After doing that, we got this. That means for a spontaneous process, delta G value will be negative. This is how we came to know delta G value will be equal to negative for spontaneous process. So for non-spontaneous process, delta G value will be equal to positive. And for equilibrium, 0. This delta G value equal to 0 for equilibrium. This you will learn in next chapter, equilibrium. So you have to remember these three values. Delta G value is negative for spontaneous. For all spontaneous process, delta G value is always negative. For all non-spontaneous process, delta G value is always positive. For the all equilibrium process, delta G value is always 0. This is how we came to know that for spontaneous. By solving this equation, we came to know that for a spontaneous process, delta G value will be always negative. So for non-spontaneous, delta G value is positive. For equilibrium, delta G value is 0. I think it's clear. Moving on to next topic. So condition for spontaneity. Next topic, conditions for spontaneity. Now according to Gibbs equation, delta G is equal to delta H minus T delta S. According to Gibbs equation, delta G is equal to delta H minus T delta S. And we know that if delta G value negative, then that indicate those processes are spontaneous. Now if delta G value positive, that indicate those processes are non-spontaneous. And delta G value 0. Delta G value 0 indicate those processes are equilibrium. Right? Now we are going to study 4 different cases and we are going to find out the values for delta G for all these 4 different cases. I'll start with case 1. Now, consider an exothermic reaction and entropy decreases. Consider case 1, an exothermic reaction and entropy decreases. For exothermic reaction, delta H value will be negative, right? Delta H value is negative, and for entropy, let it be increase. First we can consider increase case. Entropy increases. So case 1, exothermic, that is delta H value negative and entropy increases. Delta S value positive. Okay, delta S value positive. Consider first case, exothermic reaction with entropy increases. For this reaction, according to Gibbs equation, delta G is equal to delta H minus T delta S. Here delta H is negative, so delta H is negative delta H because delta H is negative. And delta S is positive, this is positive, so it is minus delta S. So minus delta H minus T delta S. What is minus 2 minus 3? You will get minus 5. Likewise, minus delta H minus T delta S. So delta G value will be negative and spontaneous. So if you consider an exothermic reaction with entropy increases, those reactions are always spontaneous because for those reaction delta G value is negative. So if you consider exothermic and entropy increase reaction, if you consider any reaction where entropy increases and those reactions are exothermic, on those cases delta G value will be always negative because exothermic delta H negative, entropy increases delta S positive. So delta G is equal to delta H minus T delta S. So delta G is equal to here delta H negative and delta S is positive. So minus T into positive delta S, minus 2 minus 3. You will get minus 5. Likewise, delta G will be negative, spontaneous. Now second case, you can consider, here we are considering exothermic, so you can consider endothermic. Entropy increases. Okay, second case you can consider entropy decreases. So endothermic, delta H value positive. Entropy decreases, delta S value negative. Entropy increases means delta S value greater than 0, that is positive. Entropy decreases means less than 0, that is negative. Entropy increases, delta S greater than 0 means increases. That's why this becomes positive. Entropy increases. Entropy decreases means delta S value decreasing, less than 0, negative. Now according to Gibbs equation, delta G is equal to delta H minus T delta S. So here delta H is positive and minus, what is T? Delta S is negative. So minus delta S. Minus T minus delta S. Minus minus you will get plus. So delta G is equal to delta H minus into minus. Here delta S is negative. So minus T into minus delta S minus minus plus delta S. What is plus 2 plus 3? You will get plus 5. So delta G will be positive, non-spontaneous. So if a reaction occurs and if that reaction is endothermic and entropy decreases, in that reaction entropy decreases, and if that reaction is endothermic, delta H will be positive, delta S entropy decrease means less than 0, that is negative. So delta G will be positive, non-spontaneous. Okay, this is case 2. So always exothermic and entropy increase reaction are always spontaneous. Always endothermic and entropy decrease reactions are always non-spontaneous. Third case, exothermics, that is delta S negative and entropy decreases. Delta S negative. Exothermic delta H negative and entropy decreases. Entropy decreases means delta H negative, right? Delta S negative. Now according to Gibbs equation, delta G is equal to delta H minus T delta S. Here delta H is negative. So minus delta H minus T into delta H also negative. So T into minus T into minus delta S, delta G is equal to minus delta H plus T delta S. Right. Now here you have to consider two important cases. Now here delta H is negative plus T delta S, right? Minus delta H here, minus delta H and plus T delta S. Now low temperature, at a low temperature, if temperature is low, this value will decrease. If this value decreases, low temperature means temperature value decreases. If temperature value decreases, the whole term will decrease. If temperature decreased, the whole term will decrease because this is temperature, T into delta S. This is T into delta S. So if temperature decreases, the whole term will decrease. At that time, delta H will be greater than T delta S. If this whole term decreases and if the decrease is less than delta H, so you can write delta H will be less than T delta S. So at a low temperature, temperature decreases, right? For example, if you consider 10 degrees Celsius and 1 degree Celsius, let the entropy be 20. What is 10 into 20? 10 into 20, 200. So T delta is 200. 10 degree into 20, 200. Now what is 1 into 20 if entropy is 20? If delta S is 20 and temperature in first case 10 degree, second case 1 degree. First case 10 into 20, 200. Second case 1 into 20, 20. That means when temperature decreased, the whole T delta S decreases, right? Now at low temperature, if T delta S value less than delta H, at low temperature, delta H value will be greater than T delta S. This will be greater than this value, right? For example, if this is minus 5 and this is, let it be 2. Sorry, let this be 5 and let this be 2. So here minus delta H plus T, let this be 5. Delta H be 5 and T delta S be 2. So 5 is greater than 2, right? 5 is greater than 2 or 2 is less than 5. So same way here, minus delta H plus T delta S at low temperature, this T delta S value decreases. So delta H will be greater than T delta S. So delta G will be, this is greater. So what happened if this is greater? Let this be 5. So 5 plus T delta S be 2. But here there is one negative sign. So minus 5 plus 2 will get minus 3. Delta G will be negative, spontaneous. So in this reaction, exothermic and entropy decreases. In this reaction, at a low temperature, delta H value will be greater than T delta S. At that time, the reaction will be spontaneous. At the same time, if the reaction proceeds at high temperature, then those reactions are not spontaneous because high temperature. Under high temperature, you can consider this case. High temperature increases, so the T delta S value increases. So delta H will be less than T delta S. Delta H will be less than T delta S. So you will get, let it be 2 and let it be 5. So minus 2 plus 5, you will get plus 3. So low temperature, in this case, low temperature favors spontaneity. High temperature favors non-spontaneity. I think it's clear. Moving on to last and final case. What is last case? Exothermic entropy decreases. So this will be endothermic and entropy decreases. So it will be increases. Endothermic, delta H value positive and entropy increases, delta S value positive. Both are positive. Endothermic, delta H value positive. Entropy increases. Increases means delta S value positive. Both are positive. So delta G is equal to delta H minus T delta S. Here delta H is positive and T delta S also positive, right? Positive. This is positive. So minus T delta S. Right? Delta S positive and delta H positive. Both are positive. Now here the reaction will be spontaneous if delta G value negative. And this will be delta G value, if delta G value is negative, then those reactions are spontaneous. and that will happen only at high temperature, because at high temperature T will be greater, so the whole term T delta will be greater, so T delta S will be greater than delta H. At high temperature, temperature value increases, the whole term increases, obviously it will be greater than delta H, so delta H less than T delta S. Now let the delta H be 2 and delta T delta S be 5, so you will get delta H be 2 and T delta S be 5, so 2 minus 5 be minus 3, so you will get negative value. So at high temperature delta H will be less than T delta S, so delta G value will be negative spontaneous. So you have to study these conditions. These are the 4 important cases. I will explain once more. According to Gibbs free energy, delta G is equal to delta H minus T delta S. Now for delta G negative for spontaneous, delta G positive for non-spontaneous, delta G 0 for equilibrium. Now we are considering 4 cases. First case, exothermic and entropy increases. Exothermic means delta H value negative. Entropy increase means greater than 0, positive. So delta G, according to Gibbs equation, delta G is equal to delta H minus T delta S. So delta G is equal to delta H is negative. So delta S positive, entropy increases means delta S positive. So we'll get delta G negative spontaneous. Now second case, endothermic, entropy decreases. Endothermic means delta H positive. Entropy decreases means less than 0. Delta S less than 0, negative. Substituting, we will get non-spontaneous. For a reaction where there is endothermic, for a reaction where entropy decreases, and if that reaction is endothermic, then the reaction is always non-spontaneous. Now third case, exothermic and entropy decreases. Delta H negative, delta S negative. Substituting, we will get delta G is equal to minus delta H plus T delta S. And this reaction will be spontaneous if temperature is low. At a low temperature, T will be low, so total T delta S will be low, so it will be less than minus delta H greater than T delta S. If this is greater, you will get delta G value negative, spontaneous. And last and final case, endothermic and entropy increases. Delta H positive, delta S positive, so delta G is equal to delta H minus T delta S. Here at high temperature, temperature value increases, T delta S value increases, so it will be greater than delta H. Since this is negative value, delta G value will be negative. Okay, if you subtract T delta S from delta H, this is greater value. If delta H is 2 and T delta is 5, 2 minus 5, you will get minus 3 spontaneous. These are the 4 important conditions. I think it's clear. Moving on to next topic, important equations in thermodynamics. So for last few hours you have seen so many equations in thermodynamics. So we are going to study once more all the equations in thermodynamics. Equation to calculate internal energy. Equation to calculate internal energy. Delta U is equal to Q plus W. This equation is known as equation for first law of thermodynamics. Second equation, delta U is equal to QV. At constant volume, constant volume, delta U is equal to QV. We have studied this equation. Third equation, delta U is equal to CV into delta T, heat capacity at constant volume into delta T. These are the equations we already studied for internal energy. Now enthalpy. For enthalpy, we discussed nearly 5 equations. First equation, delta H is equal to delta U plus P delta V. Second equation, delta H is equal to delta U plus delta NCERT, and this equation is used for gases, right? Third equation, delta H is equal to QP at constant pressure, right? Then delta H is equal to Cp delta T, heat capacity at constant pressure into delta T. Then enthalpy of reaction is calculated by sigma enthalpy of products minus summation of enthalpy of reactant. Then enthalpy of reaction can also calculate it from bond enthalpies, that is bond enthalpy of reactant minus bond enthalpy of product. We have discussed this much of equations for enthalpy. Now for work, there are two types of work, reversible and irreversible. Irreversible work, W is equal to minus P external into delta V, right? And for reversible work, we studied one equation, W is equal to minus 2.303 nRT log V2 by V1, right? We have discussed this equation. Now delta S for entropy. For entropy, we discussed one equation, delta S is equal to S2 minus S1. Another equation, delta S is equal to Q reversible by T. Now, for Gibbs equation, for Gibbs energy, we have discussed one equation, that is delta G is equal to delta H minus T delta S, right? Now for second law of thermodynamics, we discussed one equation, delta S universe is equal to delta S system plus delta S surrounding greater than 0. Okay, we have studied this much of equation in this chapter. Then heat capacity. For heat capacity, we have studied one equation, heat capacity is equal to Q by delta T. Now for specific heat capacity, small letter C is equal to Q by M into delta T. Now for molar heat capacity, C is equal to Q by N into delta T. We have studied this much of equation in this chapter. Okay, I think you remember all these equations, right? Now I have to discuss one more equation. in this chapter. And that equation is for reversible work. I have to discuss one more equation in this chapter. So these are the equations we have already discussed in this chapter. I think it's clear till here. So no doubts. So we have to discuss one more equation for reversible process. Reversible work. Okay. Reversible work. For reversible work, we have discussed one equation. W is equal to minus 2.303 nRT log V2 by V1. Okay. Now with pressure, we can express the same equation with pressure also. We know that according to Boyle's law, pressure is inversely proportional to volume, right? So by using pressure, we can express this reversible equation for reversible work. W is equal to minus 2.303 nRT log volume and pressure are inversely proportional. So instead of V2, we can write P1 by P2 because V2 inversely proportional to P2 and V1 inversely proportional to P1. So what is V2 by V1? V2 by V1 is equal to 1 by P2 by 1 by P1. That is equal to 1 by P2 into P1 by 1. So P1 by P2. So this is another equation to calculate reversible work. Instead of volume, you can use pressure also. So these are the equations we discussed in thermodynamics. I think it's clear. Moving on to next topic, third law of thermodynamics. Now, third law of thermodynamics states that the entropy of any pure crystalline substance approaches 0 as the temperature approaches 0 Kelvin. Now, consider a crystalline solid. Diamond is an example for crystalline solid. They are crystals. Sodium chloride, solid sodium chloride. They are crystalline solids. Sugar, they are crystalline solids. So, if you consider a crystalline solid, in crystalline solids, particles are closely packed. Okay, let this be the close packing of crystalline solid. So, in crystalline solid, particles are closely packed. Let this be the close packing of crystalline solid. Now, you can see gaps between their packing. They are closely packed. Anyway, there will be some gaps. They are known as interstitial voids. These positions are known as interstitial voids. If you consider a crystalline solid, in crystalline solid, particles are closely packed. Still, you can observe spaces. Okay, you can observe spaces or voids. They are known as voids. Now, according to third law, the entropy of any pure crystalline substance approach zero as the temperature above 0 Kelvin. 0 Kelvin means it is also known as absolute temperature. 0 Kelvin is also known as absolute temperature. Now, if you consider a crystalline solid, let the temperature be 298 Kelvin. Let the temperature be 298 Kelvin. At that temperature, this crystalline solid will show some disorder. Sometimes this particle may migrate from this position to this position. Sometimes this particle may migrate from this position to this position. Sometimes this particle may migrate from this position to this position. So they are showing disorder. So a crystalline solid always show disorder. They will always show disorder, and as the temperature decreases and when the temperature reaches 0 Kelvin, at that time the entropy of this crystalline solid will be 0. At 0 Kelvin, the particle will stay in their original position. At that time, the crystalline solid is having 0 entropy. The entropy of any crystalline substance approach 0 at 0 Kelvin. So this is third law. According to third law, if you consider a crystalline solid at any temperature, they will show some entropy. They will have some entropy. Like at 298 or 273 or 263 or 173 or 23 Kelvin. At any temperature, they will have some disorder or entropy in the crystalline solid. But as temperature decreases and when temperature reach to 0 Kelvin, at that temperature, the crystalline substances will be, they are highly show ordered arrangement. They will show ordered arrangement, and this ordered arrangement is observed only at 0 Kelvin. So third law of thermodynamics states that for a crystalline solid, the entropy approaches 0. Disorder becomes 0 only at 0 Kelvin or absolute temperature. The entropy of any pure crystalline substance becomes 0 as the temperature approaches 0 Kelvin or absolute temperature. I think it's clear. Moving on to next topic, measurement of delta U and delta H. Delta U is change in internal energy and delta S is change in enthalpy. Now change in internal energy and change in enthalpy is measured using an instrument called calorimeter. Change in internal energy and change in enthalpy is measured using an instrument called calorimeter, and the figure of that instruments are given in page number 169 and 170 in your NCERT textbook. Page number 169 and 170. Okay. Delta U is measured using a calorimeter known as bomb calorimeter. It is given in page number 169. Delta U, change in internal energy, is measured using an instrument called bomb calorimeter, given in page number 169. And delta H, change in enthalpy, is measured using an instrument called coffee cup calorimeter. It is given in page number 170. Delta H, change in enthalpy, is measured using an instrument called coffee cup calorimeter. So I'm not going to discuss the detailed working principle of bomb calorimeter and coffee calorimeter, because under chemistry point of view it is not important. So I'm not going to discuss the working principle of bomb calorimeter and coffee cup calorimeter. I think it's clear. So two instruments used to measure delta U and delta H are delta U bomb calorimeter and delta H is measured using coffee cup calorimeter. I think it's clear. So moving on to next one, that is extensive intensive. We already discussed extensive property and intensive property in our introductory topic. What are extensive properties? Properties which depends on amount of substance are extensive. And what are intensive property? Properties which are independent of amount of substance. They are known as intensive property. Already we have discussed this topic in our introductory topic. But after that we have seen so many thermodynamics function. So again I am going to discuss examples for these two. So again I am going to discuss all the examples in extensive and intensive. So properties which depends on amount of substance are extensive. Example, volume. volume depends on amount of substance. As amount of substance increases, volume increases. As amount of substance decreases, volume decreases, right? So volume depends on amount of substance. Mass depends on amount of substance. As amount of substance increases, mass increases. As amount of substance decreases, mass decreases. Volume, mass, internal energy. Internal energy is an extensive property. Fourth one, enthalpy. Enthalpy is an extensive property. Fifth one, entropy is an extensive property. Sixth one, Gibbs free energy. Energy is an example for extensive property. Heat capacity is an example for extensive property. Right? These are the example for extensive property. Now intensive property. Example. Temperature. Pressure. Third one. Okay, here I have to write one more example. Number of moles. These are the examples for extensive. Volume, temperature, and all the thermodynamic functions like internal energy, enthalpy, entropy, Gibbs free energy, heat capacity, number of moles. These are the examples for extensive. Now intensive, temperature, pressure. Now density. What is density? Mass by volume. Mass extensive, volume extensive. These both of them are extensive. Extensive divided by extensive, always it will become intensive. An extensive divided by another extensive. Mass, extensive property. Volume, extensive property. Extensive divided by extensive, you will get intensive. So density is intensive. Specific heat capacity. Specific heat capacity is an example for intensive property. Why? What is specific heat capacity? Formula is Q by M into delta T. Here heat is an extensive property. Work is an extensive property. Okay. So heat extensive. So C is equal to extensive by mass, extensive, temperature, intensive. Extensive by extensive, intensive. Right? Intensive by intensive, always intensive. Only you have to study this one. Extensive by extensive is always intensive. So extensive divided by extensive, you will get intensive. Intensive by intensive is always intensive. So heat capacity, intensive. Specific heat capacity, intensive. Heat capacity, extensive. Specific heat capacity, Q by M into delta T. Q in extensive. Mass, extensive, and temperature, intensive. Extensive by extensive, you will get intensive. Intensive by intensive is always intensive. So specific heat capacity, intensive. Molar heat capacity. Molar heat capacity. Molar heat capacity. Cm. Cm is equal to Cm. Heat capacity. Molar heat capacity. Cm is equal to what is Q by N into delta T. Q extensive. Number of moles extensive. Temperature intensive. Extensive by extensive, intensive. Intensive by intensive, you will get intensive. So these are the examples for extensive and intensive property. I think it's clear. Moving on to last and final topic, a relationship between equilibrium constant and Gibbs free energy change at standard state. Relationship between equilibrium constant K and Gibbs free energy change at standard state. What is Gibbs free energy change? Delta G. Delta G is Gibbs free energy change at standard state. So theta. Relation between K and delta G theta. Relation is delta G theta is equal to minus 2.303 RT log K. This is the relationship between standard Gibbs free energy change and equilibrium constant. This is the relationship between standard Gibbs free energy change and equilibrium constant. Delta G theta is equal to minus 2.303 RT log K. Now, equilibrium constant, K value, you will study K value in next chapter, equilibrium. Okay, In that chapter you will derive this equation, so I'm not giving more importance to this equation here, because next chapter, that is equilibrium, in equilibrium you will learn to derive this equation. You will learn to derive this equation in next chapter. Okay, so I'm not giving more importance to this equation in this chapter, but you have to learn this equation in the next chapter. Okay, so we have discussed so many topics in thermodynamics. I think all the topics are clear now. So thank you.